Hi everyone, I'm Laurence from Extropy. I'm here to give you a talk about the essential maths you need for zero knowledge proofs. We have a QR code here so you can get the slides for this talk. It'll direct you to a website. There's a couple of other links there as well, so you've got some other resources available for you. Let me start though by giving you an idea of my motivation for this talk. So zero knowledge proofs are a super exciting technology, and it's really useful. We're seeing it used, everywhere in Web3. But a lot of people find it a little bit scary. They're put off by some of the maths that is involved. So what I've been trying to do by giving this talk is to try to show that you can get some useful insights into how zero knowledge proofs work, and that the maths doesn't have to be quite so scary as some people think. I know people think of it as moo maths, but you can learn some of the essentials. And a lot of the problems I think that people find with the maths is because there's a lot of new terminology. So that's one of the main areas I want to address today, is to introduce what some of these terms mean, and if you're reading papers, maybe what some of the symbols mean, so that it's less of a hurdle when you're trying to find out more about how zero knowledge proofs work. Okay, so let's go. Just to mention, if you want to contact me, I'm really happy for you to do so. There's some links there to our socials. We have a Discord server as well, so you can join that. So I love this quote. This contains maths, obviously. But of course, if you don't understand something, this is not your fault. This stuff is hard, but I'm going to try and make it easier for you. Is Nobody understands it fully, so don't be surprised if there's things that you don't understand first time round. But it can be understood at some level. If you don't understand it, if I haven't explained it well, come back to me and I'll do my best to explain it further. And my advice to you when approaching this is, don't try to understand everything at once. The best idea, I think, is to get an overall feel for the area and some of the topics within the area. Maybe chunk these topics together so that rather than digging into the detail, you just get an idea of the main chunks that are needed, and then you can dig in later when you become a little bit more familiar with that. And getting familiar with the terminology is really useful. Okay, so let's start talking about numbers, and I'll introduce you to some of the terminology that you may need. So the set of integers. Now, there's a special symbol for these. It's a Z with a double slash. And these are just integers, whole numbers, the things you use to count with, and negative numbers as well. Now we can expand that as well. We can put in other types of numbers. We can have rational numbers. So these are things that, in addition, they're not able to be described by just integers. So we have ratios, we have fractions, and then we also have the real numbers shown by the R symbol. And these include other things such as pi and root 2, etc. Now, in zero knowledge maths, we really concentrate on the integers. This is because these make it easier for us. Everything works a lot easier if we just restrict ourselves to integers, and we have short, exact representations. So although in the maths you've done in school, you've probably used other numbers, you've used real numbers, etc. What we're going to be really concentrating on is the set of integers. Another area that I think you're probably familiar with is modular arithmetic, sometimes called clock maths. And this is the idea that there is a maximum value. And when we're doing arithmetic, if we get to this maximum value, then we kind of wrap around. And the real essential part of this is that we're not so interested in how many times you go around the clock. We're interested in the remainder, where the minute hand ends up on the clock. If you're a developer, you're probably familiar with this. You've probably used the mod keyword. So if we say n mod k, we simply mean the remainder when n is divided by k. So, for example, 25 mod 3 is equal to 1. 15 mod 4 is equal to 3. And if you're unsure what the remainder is going to be, remember the remainder should always be positive. Okay. Now, the next bit of the talk is going to introduce you to some concepts that are a little bit more abstract, and you probably wouldn't have come across these when you've been doing maths in school. It's not because it's so difficult to understand. I think it's more just because it is quite abstract. But it's something that is really useful when we're looking at zero knowledge proofs. You get a lot of the terminology is around these concepts. So I'm going to introduce those now. First one, group theory. And let's just sort of take this at its face value. What we do is we say, let's take a set of elements. Now, these could be anything, but we're going to take numbers and mostly we're going to be talking about integers. So we have a set of elements, whatever they are, and then as well as our elements, we have a binary operation. So an operation that takes two operands. So we're going to be taking two of those elements and doing an operation on those. In these notes, I represent this operation with a dot, but it could be anything. Now you might say, well, that's all well and good. What's the point? Well, we find out that if the group we've created, we've chosen these elements, we've chosen operation. If they have certain properties, then we can call this a group, and then that gives us all sorts of useful things that we can do as a group. So, what are these properties? Well, the first one is the idea of closure, and this makes a lot of sense because if you do an operation within the group, you want the result of that operation also to be in the group. It wouldn't make sense if it ended up being something else that you don't have in your group. So that one makes a lot of sense. The next part, associativity, well, this is just about ordering. It says we don't really care the order in which we do some operations if we do some together. Now the next two are very, very important, and they introduce some useful ideas that we're going to see a little bit more of further on. The first one is the idea of an identity. So what we say is, in our set of elements, there's a special element. Here I've represented this by the letter E. And so this identity element is used, when we use this, what it means is that when we do the operation with any element plus this identity element, then we get back the original element. So you can see there in the notes we've got E.A equals A.E, doesn't matter the order, equals A. So we started with A, we did the operation with the identity element, and we ended up with A. Okay. So there's going to be one of those in our group. And there's going to be, as we'll see later, this is really tied in with the operation that we're doing. Okay. In the groups, we only have one operation, but as we'll see later, we could have multiple operations. So that's the identity element. And then also, we want the idea of an inverse element. So if we have an element in an element in our group G, then, which I'm going to call A in this case, then we want an inverse element. So I'm going to call this one B. And what this gives us is a way to get to the identity. So if we take A, our original element, we do our operation with B, then this is going to take us back to the identity element, which is E in these notes. Okay. That's all nice and straightforward. If you want to make it a little bit more concrete, you can think of doing addition, for example. If our operation was addition, then our identity element could be 0, because when we add 0 to anything, we get the original element. And the inverse element, for say an integer, would be the negative integer, because that would take us back to 0. Now, we also have the idea of subgroups. So it could be that you've created a group, but within that group, there's also a subgroup, a set of elements that also forms a group. That's fine. Now, the next part is useful. We see this being used quite widely in ZK, which is the idea of having a generator in a cyclic group. Now, I said here a finite group. A finite group means we've got a finite number of elements. Now, what we mean by a generator is, imagine we start at some point in our group. We apply the group operation, whatever that is. That's going to take us to another element. We then apply it again, takes us to another element. If we have a generator element and we do this operation repeatedly on the generator element, what will happen is that we'll go all the way around the group. We'll get to every element within our group, and we will end up in the same place. So that explains why it's called a generator. It's generating all of the elements within our group. Now, let's take this a little further, and we'll introduce the concept of fields. Now, in a field, we have two operations. So I'm going to call these addition and multiplication. And imagine this could be the set that we have, could be integers, could be real numbers, but we're going to have two operations within our field. And again, what makes us special, what makes our choice of elements and the operation special, is that they will follow certain properties. And if they do, then that's regarded as a field. So let's just quickly talk about those properties. The first one, the associativity. Again, this is all about the order that we're doing things. It means we don't really care which order we're going to be doing the operations. And same with the second one, the commutativity as well. Now, I spoke earlier about the identity element. We have the same idea again. And this time we need an identity element for each operation. We need an identity element for addition, and we need an identity element for multiplication. So if you think about the sort of common everyday use of the addition and multiplication, you could think, well, as we saw with the group, the identity element for addition is going to be 0. That makes sense. The identity element for multiplication is 1, because when we multiply something by 1, we get the thing we started with. Okay, nice and straightforward. Inverses, we want inverses again. And we want 1 for addition, we want 1 for multiplication. Addition is nice and easy. For multiplication, again, all we're doing, we say we're going to do multiplication. If we multiply by an inverse, that will take us to the identity element. Now, that sounds fine, and it is, but you may confuse it, as I did, with thinking about division. And you might think, well, the opposite of multiplication is division, so that's how we do it. Well, that makes sense in some ways, but it can be problematic, particularly if we're thinking about integers, because if we start with a set of integers and we try to do division, we may end up something that isn't an integer. So we don't have that closure property. So the best way to think about the multiplicative inverse is just really at face value. There is some inverse element for every element within our field that will take us back to the identity. And we have there is a way to find that out for any element that we have. Okay. And then the final property there, the distribution of multiplication over addition. Again, very, very straightforward. You've no doubt seen that before. Just another property that we need. And with fields, we similarly have the idea of generators. And I'm going to talk a lot about finite fields. So this is a set of elements. The set of elements within the field is finite. We have a fixed number of those. What we commonly get is that we do this mod a prime number. So you think about a finite field where you're going to go up to a prime number. You're going to do arithmetic mod that number. Now, another piece of terminology we have is the order of the field. This is just the number of the elements in the field set. And it turns out that for a finite field, the order is either going to be prime, so we have a prime number of elements, and we call it a prime field, or the power of a prime, which is called an extension field. Now, there's nothing intuitive about this. At first glance, there's no obvious reason why this would be the case. But I'll just explain that we need this because without this, we wouldn't have multiplicative inverses. So it's really a case of if we want something to be a field, then we need this property here. So as an example, if we take a set of integers, we could have 0, 1, ... up to p minus 1, where p is a prime number, and this will give us a nice simple finite field. Again, we have generators, and the generator is capable of generating all of the elements in the set by repeatedly doing the field operation. So what we often see in articles, we call a generator G, and then we repeatedly do an operation. And when we do this, we write it down as exponentiating. So we have G to the 0, so they're going to be the identity element, G to the 1, which is G, G squared, which is G times G, etc. And that will give us all of the elements within our field. If you want a toy example of this to practice with, you can use a very small set of integers. So here we've got the group 0, 1, 2, 3, 4. We're doing modular arithmetic. The prime number here is 5. Now, that terminology, that symbol, the way it's written like that is because the Z is there to show we're dealing with integers. The 5 at the bottom, the subscript, that is showing us the prime number that we're using to do our modular arithmetic. And then the asterisk we have at the top, that is saying that this is going to have multiplicative inverses. And you'll see this again, widely used within articles about CK. Okay. If you want to try it out, we've got details there. We've got details of the generators there as well. We've got two generators, 2 and 3, and you can try it out. Do operations with 2 and 3, and you'll get back all of the elements within the set. Okay. Okay, let's change topic now and look at complexity theory. Now, this is super interesting in its own right, but also it's quite fundamental to zero-knowledge proofs. And what it's about is to look at the time or space requirements we have to solve a problem. So there are lots of problems out there that mathematicians and computer scientists are interested in, and they start to think, well, can we group these together? Do they have similarities? Do they, are there things that we can say? We can say these types of problems are similar in some way. And when we're looking at them, what we often do is look at the time needed to solve a problem in terms of the size of the input. Now, a great example of this, or very commonly given example, is the idea of a traveling salesman. The idea that we have a salesman traveling between cities, and we're trying to decide whether the route he has chosen is really the optimum route. Now, you can imagine that if the number of cities we've got is very small, say 3, this is quite a simple problem to solve. We can probably answer that thing quite simply. Where it gets more difficult is when we increase the number of cities that we have. And the input in this case is the number of cities. So what we're looking at is how long does it take to make this decision, to decide whether this is an optimal route, given the number of cities that he is going to be visiting. And what we find is that quite quickly, as we increase the number of cities, as we increase the input, making this decision becomes quite unfeasible, quite difficult to decide. Now, the terminology with this, we often talk about the input, we often use the letter N for the input. And we try to group together problems, classifying them according to how the time taken to find a solution varies according to N. Now, we always look at the worst case, and it could be that the time taken to decide about this would vary according to a polynomial of n. So this is n to some power. So where I've said k here, where this is some constant value, maybe 2 or 3, some small value. Now that may seem like a lot, but actually these are some of the easiest solutions. So we say that if this is the case, if we can indeed vary the input n according to this constant, and then decide, that gives us the time to decide the problem. These problems are seen as tractable. They're not too difficult to solve. And these are called polynomial problems, or solvable in polynomial time. And where this comes in, where we have a particular intersection with zero knowledge as well, where we start to think about, well, if we have a solution to a problem, how long does it take to verify that solution? So taking the traveling salesman problem, if I produced a route that he is taking and said, that is his route, how long would it take you to decide whether that was an optimal route or not? So strictly speaking, when we're doing this, we will do this as what's called a decision problem. So you need a yes or a no answer, but we don't need to be too concerned about that. So that's the background. What we find when we look at all of these types of problems, well, we get some classes, and I've shown you 2 possibilities here, the left and the right possibility. And these classes are known by initials, so P, NP, or NP hard, NP complete, etc. The reason we've got 2 is that there's an open debate whether the class of problems P is the same as the class of problems NP, and nobody knows the answer to this. It's thought it's probably not the case, so we're probably on the left-hand diagram here, but nobody knows for sure at the moment. Let's talk a little bit more about these classes. So I've already mentioned the class P. This is a class where when we have a problem, we can solve that in polynomial time, and the answer can be decided in polynomial time. Now, NP, the next kind of most important class, is one where we can, once we have a solution, that solution can be verified in polynomial time. Now, I'm not saying how long it takes to find the solution. And really, what we're going to say is that, well, that solution is going to be hard to find. It's going to take us a long time to find a solution, but hopefully we can then check that solution fairly quickly. And this is a really useful concept. This idea of being able to do some computation, but being able to check the accuracy of that, to check a proof of that very quickly, is really essential, really at the heart of zero knowledge proofs. Okay. Now, if you want a good example of this, think of someone who has a secret key, and they've encrypted some text. Now, if you're provided with this encrypted text and you don't know the key, it'll take you a long time to decrypt that. You'd have to brute force this and just try every possible key until you found one that worked. It'll take you a long time. But if I give you the solution, if I give you the key and say to you, is that the correct key? Well, you can check that very quickly. You can just decrypt it, and if it comes out something sensible, there you go. That's going to be the key. So here we have an example of an NP problem, where to get the solution is hard. It's going to take a long time, but to check the solution is going to be very quick. Now, I'm not going to go through the rest of these classes very much. It's worth reading up about, but yeah, we don't really have time for that. But what I just will say is that we also have the idea of transformations. So we can transform these problems from one into another, which can be very useful. But this transformation needs to happen within polynomial time. And if we can do that transformation, then we have the NP-complete class. Okay. I'll skip over the NP-hard, but I want to mention the IP class, because this is very relevant to zero-knowledge proofs. This is the interactive proof class. And this came about when people were thinking about mathematical proofs. Previously, you would get your proof by starting with some axioms, following some logical steps, and at the end of that, you would have some statement that was the thing you were aiming for, and you could say, there's my proof. What they did with the idea of interactive proofs is to say, well, let's change that around a bit. Let's try having someone else involved. Let's try somebody who can ask questions of the proof. So there's some interaction going on. Also, why don't we have the possibility of some randomness as well? We can use randomness in our proof to prevent the prover cheating and producing a false proof. And this gives us the class of problems IP. Some great videos by Alessandro Chiesa, and there's a link there if you want to have a look at those. Okay. Now, another reason that complexity theory is useful is some of the notation, which is called the big O notation, which is used to describe this complexity. It's a shorthand way we have to be able to compare, for example, different types of proving systems. And so with the big O notation, we have the capital O, then we provide the input. And so here we're saying, for example, O of n squared. What this means is the n here represents the input. We're saying n squared. So what we're saying is that the time taken to verify the solution will vary according to the square of the size of the input. Now, as you remember from that, that's going to be a polynomial, or that could be NP if we're talking about showing the time taken to verify the solution. N squared is not bad. Obviously, if we have something like root n, that's even better. But these are seen as reasonable. If you start to get, say, 2 to the n, then that's much worse. That's going to take much longer. But we use this notation very widely. And I've got an example here. This table is quite old, but it shows you some different types of proving systems and some aspects of those systems. So, for example, if we have a look at the proof size here, we've got big O of 1 for the SNARK type of proving systems. This means we don't care about the input size. It's a constant size proof. But for the SNARK systems, it does matter the input size. So that the proof size will grow as the size of the problem grows, etc. Now, some of these estimates, particularly to do with the gas cost, are no longer true because Ethereum has moved on a lot since then. But it's just to give you an idea of this big O notation. Okay, let's move on. I'm going to talk now about elliptic curves. Now, no doubt you've heard about these. You've seen diagrams of these. These are special curves. They have an equation similar to this, similar to y squared equals x cubed plus ax plus b, where a and b are constants. Now, what's interesting, why we like elliptic curves, is they have this special property which seems almost too good to be true in a way, but the points on the curve satisfy the group axiom. So the points on an elliptic curve form a group, which is not at all obvious that that would be the case, but that is the case. So what that means is that if our group operation is addition, then we can take 2 points on our curve, add them together, and that will give another point which is also on the curve. That has to be the case because the group property of closure is needed. So that we get that because this is a group. And we have the idea of an identity element as well. This is called the points infinity. This is an extra element that is added to our group to make everything work. Okay. Now, this is usually represented geometrically by a nice diagram. This we're adding points P and Q, and this ends up with this point R down at the bottom here, which is P plus Q. That's what it looks like. Now, addition might not be addition in the usual sense of the word. We can define that however we like. But we can do this on elliptic curves. I'm going to skip over some of these details here, but they're there in the notes for you. Now, that's addition. We quite like to do multiplication as well, but this is the group we're talking about. We've only got one operation, so we're a bit stuck, but what we can do is something called scalar multiplication. And this is a way that we can effectively get multiplication. It's not difficult to see how we do this because multiplication can be seen as doing addition a certain number of times. So what we can do, if we want to multiply a point by a scalar value, so in this case I'm going to call this one k, want to multiply a point p by k, then all we have to do is add p to itself k times, and that is the same as if we were trying to do multiplication. So that's what scalar multiplication is all about. Roots of unity, you will come across this term. This is points on our curve, part of this group, where if we add them together, if we add them to themselves a certain number of times, we are going to get the identity element. The identity element is often called O in elliptic curves, so that's why I got it here. So in this equation, you see we've got some points P, we're adding it to itself n times, and this comes out, well, I put it there as 1, it could be O, but it's the identity element. And if that's the case, then our point P is going to be called a root of unity. You also get this in other areas of maths as well, in complex numbers, etc. But this is useful in elliptic curves and in CK. You may well come across this, and that's what that is, what roots of unity are all about. Okay. I'm going to skip over this visualization and introduce something a little bit more complex now, which is elliptic curve pairing. Now, there's an article linked there from Vitalik that you can have a read of, but this is a much more complex area, but it is quite fundamental to how some zero knowledge proofs work. So I'm just going to try and explain the basics of this and give you an idea of what is meant by pairing. So pairing is also called a bilinear map. I'm going to say what bilinear means, but think of this idea of a map. It's a way to move between different structures. So we like groups, we understand groups. So let's talk about groups. Say we've got 3 groups, G1, G2, and G2 here. Okay. What we're talking about with pairing with this bilinear map is a way that we can take elements from G1 and G2, and then that those will map to some element within G2, within our third group. Okay. Now, if our group has pairing, now particularly thinking about elliptic curves here, and the points on elliptic curves which are forming groups. If those elliptic curves allow pairing, then we will get this property. And this property, this is built by linearity. This is the idea that you can map these to a third group. The other point here, non-degeneracy, is just to say that there's a trivial case which we're going to avoid. Okay. Now, I'm not going to go through all of this. It gets a little bit more complex, but it's just all about a technique and the fact that this is a property that we can have with groups that we may want to use. Okay, so this is some property that holds between groups and allows us to take elements from some groups and then find corresponding elements within a third group. Okay. And often we use this with polynomials as well. As I say here, the form of the function that we're doing to do this mapping can be quite complex. So I won't go into that any further, but that's what that's what we mean when we talk about pairing within elliptic curves. There's this useful property that they exhibit. Why this is useful in zero knowledge is that we often want to be able to verify relations between inputs and outputs of our zero knowledge proof, particularly these things called circuits. I'll come on to what those are. But we often want to show that there is a correct relationship between those. And to be able to do that without revealing inputs, well, this is where we're starting to get all the aspects of ZK. We're getting the idea of a proof, the fact that we can show this relationship is correct. We've got the zero knowledge because we're not revealing the inputs themselves. Okay. So let me move on. Now, if you study ZK at all, you'll know that polynomials are really everywhere within ZK proofs. And this is not too bad because polynomials are probably something that you've come across before. And you've probably covered them in school, you've probably had practice at finding the roots of polynomials. They are really useful mathematical objects. And they have this typical form, like something like 3x squared plus 4x plus 3. We have terms involving a variable, in this case x. We can have more than one variable. We can have multivariate polynomials. I'm just going to talk about single variable polynomials here, but they can be multiple ones. And they can contain a lot of information. Now, this one, you might think, well, there's not much information in that. But when we use these in zero knowledge proofs, we often have polynomials that have tens of millions of terms. So you can appreciate, in that case, there's lots of information held within them. And also we can write equations involving polynomials. We often use capital letters to represent polynomials. So I've got some here, polynomial A, polynomial B, polynomial C. And if we can say that A plus B equals C, then that means that that's going to be true for any value of the variable x that these polynomials have. And again, that's quite a powerful thing that we can do. Now, arithmetic on polynomials is quite straightforward, thankfully. It's a great thing. There's a link there to details about that, but it pretty much works as you would expect. Let me talk about roots of polynomials. You've probably at school had to find roots of a polynomial. The root of a polynomial means that that's the value of the variable x for which the evaluation of the polynomial turns out to be 0. Okay, so here we've got a polynomial p. We have the value r. We're going to evaluate the polynomial at r, and that's going to be equal to 0. So that means that r is the root of that particular polynomial. Okay. Now, there is a kind of a technique that is widely used in zero knowledge proofs, which is a way of decomposing polynomials. And what we can do is that if we start with a polynomial p, and we know that it has a root, so that root is going to be represented by r, then we can rewrite that polynomial in this sort of form. We can say x minus r times then some other polynomial. So here the other polynomial is q of x. So that's something we can do. We can effectively take our original polynomial and break it into two terms of this form. I haven't mentioned what I mean by degree. This is looking at the power of x that we have within our polynomial. And hopefully it's kind of makes sense that if we take this term x minus r outside of our p of x, so we're left with this q of x polynomial, then q of x is going to have degree 1 less than our original polynomial because we've taken an x out there and it's in the term at the front. Now, coming to one of the most important ideas in ZK, and this is the Schwarz-Zippel lemma, and this can be expressed in different ways. And the reason that it's useful in zero knowledge proofs is that in ZK, what we want, we have a prover and a verifier. The verifier is going to be checking that the prover has a correct proof. Now, we want this to be simple and straightforward and quick. Okay? We want the verifier to be able to make the decision about the proof very easily, very quickly, very succinctly. Okay? And polynomials really help us with that. And what I'm going to start off by saying is imagine that the prover has somehow represented their proof in terms of a polynomial. And the verifier knows some details about what a correct proof should look like, what a polynomial of a correct proof should be like. They may not know it exactly, but they may know some properties of it or some details about it. Now, if I said to you that I've got two polynomials, and here we've got them drawn out, so it's really obvious that they're different. But if we didn't have them drawn out, if you didn't know the equations, if I said I had two different polynomials, maybe I know how to evaluate these polynomials, then, and I wanted you to check whether they're the same or not, well, we can do this by evaluation. So we can evaluate our two polynomials. Now, we could get two situations. When we evaluate them, maybe those evaluations are going to be the same. So here we've got at 0.10, these two polynomials evaluate to the same result, which is 0. Now, if I said that, if you found that out, then you may say, well, perhaps these polynomials are the same. They evaluate to the same point here, so maybe they're the same. But what's interesting, what's useful about the Schwarz-Zippel lemma is that it's really hard to find, it's very unlikely that you will get this situation. If polynomials are different and you evaluate those polynomials at a particular point, it's very likely those evaluations are going to end up being different. So this is great for the verifier. If he wants to know whether two polynomials are different, he's not going to have to ask many questions. He's not going to have to do too many evaluations to get to the point where the evaluations end up being different. So this is really expressed here. So we're saying here are polynomials I'm representing by two functions, f of x and g of x. If they're different, then pretty much any x value that you plug into one of these functions, to one of these polynomials, is going to give you a different result. So this gives us a nice, easy way to check, because it's very unlikely we're going to pick a value of x where they do in fact come to the same evaluation. Okay. Now, I'm not going to go through what it means about them being equal, just to say that because we're doing modular arithmetic on finite fields, sometimes it's not quite so straightforward as you might think to check whether they are equal by inspection, but by evaluation, it makes a lot more sense. But let's look at some of the ways that we can describe polynomials. So within a graph, within this, for example, we see this. This is showing the points of a polynomial, but we could also have the equation of a polynomial, the 3x squared. And these values, the 3 for the x squared, the 4 for the x, these are the coefficients of the polynomial. So we have two possible ways of representing a polynomial: the equation or the points that we get when we evaluate that polynomial. And we can move between these two representations. So the way to move between the points to get back to the coefficients is by a process called interpolation, which is what I'm showing here. So if I gave you these red points, you could do interpolation, and that would give you the equation of this curve that you can see there. And then to get back to the point value, we then do evaluation of the polynomial once we know the coefficients, and that gives us the points. So we can move between those two representations. Now, an important concept, a nice way to think about what's happening with ZK, is the idea of transforming our proof, transforming things between different structures. So we could start off with a prover making some kind of statement, such as, I know the square root of 25, and then from that's not really easy to use. So what we would probably want to do is to transform that into things that are going to be easy to verify. And to cut a long story short, what we do is we do some transformations which end up with polynomials. But when we're doing those transformations, it's important that at each whenever we do a transformation, we're doing that correctly. We still have the correctness of that. So the prover cannot cheat in any way. And in fact, the process we end up with between the prover and the verifier, we have in zero knowledge proofs, we have an interactive idea of the proof, where the prover has made some claim, the verifier wants to check that. The verifier can check this by choosing random values and asking the prover to evaluate a polynomial at that particular value. Now, if the verifier chooses these values at random from a sufficiently large choice, from a very large finite field, then this gives us some useful properties. What this means is that they can very quickly decide whether this proof is correct or not. They don't have to do lots of evaluations. They can very quickly decide whether the proof is correct. Okay. I'm going to move on because I'm short of time. So I want to talk about polynomial commitment schemes. This leads on from the idea of using polynomials. The problem, if we represented our proof as a polynomial, first of all, that would be a very large polynomial, lots of terms. Now, the prover could do that and give that to the verifier and say, there's the proof, is that okay? But we don't want that for a couple of reasons. The first reason is that the amount of information there is huge. So getting that information to the verifier, getting the verifier to do all that evaluation is going to be too much. We want a succinct proof. We want this to be quick and easy to do. We want to be able to send these proofs over a network. We want these proofs to be small. So we don't want to send a massive polynomial to the verifier. The second point is the zero knowledge aspect. The prover will have some private inputs to their proof that they don't want the verifier to know. If they sent across all the information, then maybe the verifier could reverse engineer the polynomial and work out the secret inputs. So we don't want that. So what we do instead is we have the idea of polynomial commitment schemes. Now, we know about polynomials already. You've probably come across commitment schemes. This is the idea. Some function allows us to commit to maybe a value, or in our case, we're going to commit to a polynomial. But once we've committed to that, we can't change our mind. And so what we're going to have is the prover committing to a polynomial, or maybe a set of polynomials. Once they've done that, and then given those to the verifier, they can't change their mind. The verifier can then get evaluations of these polynomials, and they can choose these evaluations at random points. But because of the commitment, the prover can't then change what they've given the verifier to fit what the verifier has asked for in a way that would disguise the proof if it was incorrect. So it's really to stop cheating. And then the other point about commitment schemes, if you think of something like a hash function, is this gives us a very succinct representation. If that's the case with polynomial commitment schemes, we have a succinct representation that can be available to the verifier so that we don't have to pass a huge amount of information. And coming back to some of the ideas about succinctness and ease of verifying things, one point that we have shown by this equation here. If you imagine we have an equation with some polynomials, we've got 4 polynomials here, P, Q, R, and S, and we say that we found some value of Z for which P of Z times Q of Z plus R of Z equals S of Z plus 5. Now, if that's true for a particular value of Z, it's overwhelmingly likely that that is true in general for any value that we put into these polynomials, which is amazing. That's a great result, and perhaps a little surprising. That all comes back to the Schwarz-Zippel lemma and the properties of polynomials. So it means that the verifier can check some polynomials at a particular value of Z and then generalize that and say, well, it worked for this value, it's probably going to be true for any value, so I don't have to check all those other values. Okay. Now, I've really mentioned already some of the properties here. So the idea of binding, once we've got a commitment, we're committing to that, we can't change our mind. And also we've got the idea of hiding. So that's the idea that for the prover, they're hiding information. The verifier can't find out too much information. Now, there are different types of polynomial correctness schemes. I won't go through them in much detail here. We don't have much time. But I've got some links there. There's a great ZKP study group video about these. But yeah, you've got the different types there showing some of the properties, how useful they are for the different types. And some of the common types, the hash function types, these are the ones that are used by Starks. The pairing groups, these are often the ones used by snarks. And they have advantages and disadvantages. So the Stark ones based on hash functions, they're post-quantum, for example. They would work even with quantum computers. But where the Stark type ones aren't so good is, for example, with the proof size. So you can see here the pairing group, these are the snark, a lot of the snark ones, we have a fixed size proof. Okay, let me move on. I think we don't have a lot of time, so I'll just quickly mention error correcting codes. This is the idea of introducing redundancy into some message that we have. So if you send a message, it could get garbled in its transmission before it hits the receiver. A way to get around that is to add redundancy so that the receiver, if he gets a garbled message, can reconstruct the original message because there's redundancy in the message. A particular way, a particular example of that is the idea of Reed-Solomon codes. There's some details here. I won't go through that, but you can have a look. These are used outside ZK, but they're valuable within zero-knowledge proofs as well. Now, one point, or the way that they work, that we can construct these, is using polynomials. Polynomials are a great general purpose mathematical structure. The way that we can create a way of doing error correction is by representing our message as coefficients in a polynomial. We can then add redundancy by evaluating that polynomial at many points. And if we have enough evaluations, then what that means is that even if we lose some of those evaluations, someone can use the other points that they have to reconstruct the polynomial, and that will give them the original message. Okay. So as you can see here, we could start off maybe our original, we originally have points from x1 to xd here. But once we've done that and we've created a polynomial, we can extend that and we can use other points on the polynomial outside our original range, which is going to help us with redundancy. Okay. And the reason that they are good in zero-knowledge proofs is that they amplify errors. And this is particularly used within Starks. So within Starks, we represent computations as polynomials. And then we can easily see whether there are errors. So if the prover provides some polynomials, which is not a correct representation of a computation, then the errors that are there within the polynomial are effectively amplified, could easily be seen by the verifier because of the fact that we're using Reed-Solomon codes. Okay. Let me move on. So I'll talk quickly about another concept that you may come across called the inner product argument. So this is particularly used in a type of proof called bullet proofs. And this is a little bit different to the things we've covered so far. It's to do with vectors, and you may have used vectors in your sort of school maths. Vectors are sets of numbers. The inner product is an operation that we can do upon two vectors. This takes takes two vectors and returns a scalar. So we start off with a set of numbers, or two sets of numbers, and this inner product will give us one number as a result. And it's a way to see whether these vectors, what sort of relationship these vectors have with each other. Maybe they're completely independent, or maybe they're related in some way. And this is shown to us by the inner product argument. So that's what inner product means generally. But we can extend that, and well, we can also bring in polynomials and end up with, if we, for example, have a vector which is formed by taking powers of some number. So here we're starting a number z. If we're taking powers of that, then the inner product is representing the evaluation of a polynomial. And this, if you follow through with this equation here, you will see, effectively, this is what a polynomial looks like. So we have, our x here raised to some power, multiplied by some coefficient, adding all those together. Well, that's really what a polynomial looks like. Now, how these are used? Well, to other points we need to think about. I've spoken about elliptic curves, the fact that the points on an elliptic curve form a group. We also have the idea of generators. And we can form commitments to points on curves, as you can see here. And what the idea of the binding commitment means that if we do this, if we get a commitment to particular numbers from a curve, then we couldn't find any other numbers that would give us that commitment. That's the binding property of commitments. And we can extend that to vectors. If we have the coefficients here in a vector, we can form a commitment to that, and then that is going to be binding. And why this is useful in ZK is that we use the inner product to show relationships between vectors, and really to enforce those relationships, and to say that these things need to be true if the proof is correct. And why it is useful is that we can take something that is quite complex, quite large, and then reduce that in size. Remember, we want this process to be very succinct. We want the verifier to be able to check this very quickly. And with the inner product argument in, say, in bullet proofs, what we can do is start out with very large vectors, but then effectively reduce the size of these at different steps. But at each time we're doing this, we're checking this and showing that the inner product argument, the relationships between these vectors, is correct. But we can keep reducing the size of this. So at the end of this, we have something much simpler to check. So the verifier doesn't have to spend so much time checking. It doesn't have to use so much information. There's a lot of more information about that. There's a link there to an article. But this is really just to give you an idea. If you come across this term, the inner product argument, that's why it's useful. It's a way to, it's really a way of enforcing the relationships between some details of our proof, so that this can be easily checked by a verifier. Okay, I'm pretty much out of time, so I just wanted to mention where you can go next if you want to find out more about this. We have a link there to our Awesome Maths repo, which should tell you more. There's an article I wrote about the MENA proving system, or one of their proving systems called Kimchi, that you may want to have a look at. I tried to introduce this in a way that didn't require too much mathematical background, so hopefully that should be understandable to you. We also do a lot of work on the ZKML, and we're involved in teaching a number of boot camps. So there's a link there to some of the boot camps that we teach around zero-knowledge proofs and also around ZKML. Also, if you want to join our Discord server, you can do that. There's a link to that there. We may well provide some further resources around maths. We're going to try and do maybe some kind of agent that will help you, that you can ask questions about some of these topics, that will give you some friendly answers that should help to introduce these topics for you. Okay, so let me just go back to the beginning here. So that's the link that will take you to these notes. Again, they're also available on our website, which is maths.extropy.io. Also a single PDF if you want that link there. I hope that's been useful for you. I hope that's taken away some of the the mystique about the maths, some of the complexity about it, and hopefully persuaded you that although there's a lot of maths involved in zero knowledge proofs, it's worth trying it out, it's worth looking into, and that if you get to grips with some of the terminology and get to understand some of these concepts a little, then this should give you some insights into zero knowledge proofs generally. So thank you for listening. Thank you to our host today for hosting this event, a great event, actually in a brewery here at Denver. But that's the end of that. Thank you very much, everyone. I hope that's been useful, and please do get in touch if you would like to. Thanks, everyone. Bye bye.